Hello and welcome to today's webinar, The Basics of Condition Monitoring by Balluff. My name is Tom Knauer. I'm the Global Manager for Robotics and Automation in Strategic Marketing. And we're going to take you through some of the basics of condition monitoring, what it is, and some best practices and so on. I'll give you a little bit of an overview of the agenda. We'll talk about some trends and what's going on with customers. What is condition monitoring? A quick overview. What people typically monitor based on some studies that we've done and some of our publications that we work with. A little bit about solutions, and then how you might get started with condition monitoring. So let's go forward. What are some of the trends and challenges? What are things that are driving the industry right now, and why are people starting to consider condition monitoring and predictive maintenance as important factors? So some of the key trends that are going on that we're seeing, and most of the industry talks about quite a bit, are these megatrends. Digitalization, both in our production but also with our customers. Digital technologies are taking over our lives and becoming more and more important. A lot of changes are going on in the workforce. We have workers retiring, we have shortages of workers, and we have different skill sets of new workers that are coming into the workforce nowadays. Lots of increasing automation and productivity to address the challenges that are out there. We have what we call mass customization, where we have high volume, low mix, but also low mix and high volume, and we need to make production flexible to be able to adapt to these changes. We have pressures to reduce cost, to reduce footprint, to reduce emissions, and so on. And then finally, the supply chain issues that were exacerbated by the Corona and COVID crisis that mean that more and more companies are looking to produce closer to the point of consumption and to reduce their supply chains to address these issues. What does this mean? More robotics and automation. More smart devices are required. Communications and networking required to interface those devices. And now we see software and AI is emerging to help address a lot of these automation challenges. And all of this, of course, has been accelerated by the Corona and COVID crisis. In general, we see that the market for factory automation is large and growing rapidly, significantly faster than the economy overall. There's a lot of different segments automation that are using automation. Automotive, packaging, food and beverage, general factory automation, intralogistics, material handling and warehousing. All these areas are using automation more and more to address the challenges and to produce more efficiently and more quickly. The key topics that are being driven by these main issues are things like smart devices, cybersecurity, robotics and collaborative robots, software, digital twins, and so on. These are all kind of the big things that are happening out there in the marketplace and in industrial automation. So what does this mean? In general, manufacturers need to be much more efficient and get much more out of their equipment. So we start talking about things like overall equipment effectiveness, uptime, and productivity. So how does this tie into what we're going to talk about today? Well, the efficiency goals that we see manufacturers driving relate to various different subtopics. We see, as I mentioned before, a total focus on reduction of costs, improved quality, overall equipment effectiveness, reducing unplanned downtime and small stops. By addressing condition monitoring and predictive maintenance, customers can start to help attain these goals and again, move towards a more efficient, more cost-effective factory. So why condition monitoring and predictive maintenance? Well, there are various studies out there that show that downtime is really costing a lot of money when it occurs, and it's becoming more and more of an economic problem for many factories. One study shows around $17,000 per incident of downtime. That's a lot of cost. 800 hours per year in a typical factory of downtime. Or in the automotive world, $22,000 a minute of downtime due to the cost of lost production, due to the cost of the equipment, due to the cost of service and maintenance. All these costs are driving manufacturers to try to address this unplanned downtime issue that's pervasive throughout the industry, whether you're in automotive production, food and beverage, life sciences, or other industries. We went out and we talked to a wide range of customers in these different industries. And what we found when we asked them about what keeps them awake at night, what's their big challenge, number one problem was unplanned machine breakdowns. Related to that were several subtopics, the long downtimes associated with those unplanned downtimes, either to get the parts that may not be on the shelf, or to do the actual repairs, or in general, just the general disruption to the factory process. In many cases, these machines and pieces of equipment can be in hard to reach places, up high on top of the factory or on top of a large machine tool, or in a cage locked away so that they're inaccessible to general people. It takes time to get there and to do inspections and so on. Plus, the other factor that we see is the need for more machine condition data as part of the general IoT initiatives and the broader trend to improve digitalization in the factory. What does this mean? Lost production plus lost capacity plus lost machine availability means lost revenue to you and the manufacturers out there. So what is condition monitoring? From a very broad level, the basics of condition monitoring is really a system to monitor the status and health of the machine, a piece of equipment, the overall manufacturing plant, and the subcomponents that compose those, whether it's a gearbox, a drive, a motor, or some other part that is a critical part of that machine. The idea is that we want to monitor that equipment. And even more importantly, if we can do that on a continuous basis rather than a one-time basis, we can start to detect the changes and anomalies that occur, and then secondly, record those over time to start looking for trends and things that will help us understand what's happening on a machine for long-term evaluation and long-term trend tracking. So now let's talk a little bit about how people do maintenance. We call this the maintenance continuum. And there's 4 basic maintenance philosophies that we see out there. The first is what we call reactive. That approach basically is where we talk about a run to failure. You just run a piece of equipment or machinery until it breaks, and then you go out and fix it. In this case, the preventative maintenance costs are very low. You're not sending people out to service it until you actually have something break. That side of the equation, though, can be very expensive. The cost of time of the maintenance people to fix things, the cost of time of parts, or the cost of the catastrophic failure itself. The next approach that's a little more sophisticated is preventative maintenance. This is where you have regular maintenance intervals. You go out and send your team to change the oil, change a filter, do inspections, and so on a regular basis. We generally have better availability and better longevity of the equipment because we are trying to address some of the issues that might cause a failure, and a little bit higher maintenance costs than the reactive approach. The next approach, more sophisticated, is condition-based. This is based on actually monitoring the condition of the machine and trying to get the machine to start telling us, or the piece of equipment to start telling us when a failure may be occurring. This really starts to improve the efficiency of the machine, the uptime of the machine, but also can potentially reduce your maintenance costs because you're only providing maintenance on a machine when that machine is starting to fail. You're not just sending people out to fix a machine whether or not it's broken and do maintenance whether or not it's broken. And then the final, most sophisticated approach is what we call predictive analytics, where we really start to analyze the condition-based data that's bringing out and look for trends and patterns and start to try to get a warning far ahead of time before a failure may occur so that we can do the maintenance on the machine before the machine requires us to do the maintenance on it. That means that we can schedule it so that when there's a weekend and the machine is scheduled for downtime anyway, we can fix things and address things and so on. It's a much more proactive approach. So our goal in general is to try to move people up this continuum from reactive and preventative maintenance to a condition-based and a predictive approach, which will allow much more sophisticated and much more addressing of the issues and the challenges that might occur with a machine and that might cause this unplanned downtime. So what does this look like in reality? We have here a graph of vibration data on a machine over the period of about a year. And as you can see, the performance is relatively stable until we start to go towards a failure and a breakdown, the red part of the curve indicating a catastrophic failure. And we've highlighted a period of about 2 months of data here where you can start to see things start to move out of spec, but not yet quite into the failure mode. So each of our different maintenance approaches addresses a different part of this situation. How would reactive maintenance approach this? Reactive is really only going to take place when you actually start to see the machine breaking down and things are gone too far, and you're really just at this point fixing a completely broken machine and completely broken process. Preventative maintenance goes out and looks at regular intervals, in this case about every 3 months, and does preventative maintenance on that machine. The challenge being is that that preventative maintenance may or may not address that impending issue and may or may not occur at the right time. In this case, you can see the last maintenance cycle occurred before things really started to go bad, and so the timing on that maintenance cycle wasn't necessarily perfect to address the issue. Condition-based monitoring starts to look at the specific vibration pattern here and will start to address and start to send warnings when you exceed a specific limit. The challenge here is setting that limit at the right level and recognizing that alarm and then taking action. In this case, the limit that was set gave about a week to 2 weeks worth of warning before the catastrophic failure, so there would have been some time to address this issue. You can also see, though, that there were several peaks in the vibration spikes that got close to but didn't exceed the limit. So you potentially could have had maybe 4 weeks notice before the failure occurred to start thinking about looking at that machine, doing an inspection, and start planning your maintenance before the failure actually occurred. The final approach, predictive maintenance, looks at the whole set of data and starts to analyze trends. And just from an outside perspective, taking a look at this, you could probably say about 8 to 9 months in, things are starting to get a little bit out of control, and you can have either people doing the analysis or even use software tools that would probably start to tell you that somewhere about 8 or 9 months into the process, you need to start doing some analysis more deeply on the machine, looking at things and starting to understand what the problem might be, taking action far before that potentially catastrophic failure takes place. So this kind of gives you a quick graphic overview of the 4 different approaches and how they might be applied in a real-life situation. So how do machines fail? There's basically 2 different types of main failures. The first is age-related. So if you think about your car, as things get older, there's a clear correlation between the failure of certain parts of the car. So for example, in this picture here, you see the rust. The body starts to deteriorate with age. The tires start to deteriorate with age. So preventative maintenance can help address those. You can take the car to the paint shop. You can wash it regularly. You can replace the tires at certain intervals. Preventative maintenance is good at addressing those age-related failures. On the other hand, the majority of failures are non-age related. These are more evenly spread out over the life of the asset, and they can occur for a variety of reasons. Things like operator error or improper installation or running it too hard. So if we talk about our car, operator error, the driver crashes the car. That's a non-age related failure. Or you drive the engine too hard. That's again a non-age related failure that could cause premature failure that would likely not be addressed by preventative maintenance. And so if we look at these 2 different types of failure, it's pretty clear that the large majority of failures, based on the studies that we've looked at from the US Navy, United Airlines, and some other sources, indicate that at least 80% of failures are non-age related and therefore would not be addressed by preventative maintenance. So the age-related failures fall into 3 main types, but you can see the general profile here is that as the asset gets older, the likelihood of failure increases more. The non-age-related failures, after an initial period, are all relatively flat. That means that the failures have a similar likelihood of occurring early or late in the process. Again, 3 different types of failures, but the key thing here is that the non-age-related failures are the majority of failures compared to the age-related failures. So what does this mean for our approaches, maintenance approaches? So if we look at the age-related failures, generally preventative maintenance is very good at addressing them, but it doesn't address non-age-related failures. Condition-based monitoring can address both the non-age-related failures and the age-related failures. And then finally, predictive maintenance can address both non-age-related failures and age-related failures also. So the point here is that by moving towards a condition-based or a predictive approach, you can start to address both the non-age-related failures and the age-related failures rather than just relying on a preventative maintenance program which may not address most of your failures. So how do failures happen? Well, this gives a rough outline of the typical life cycle of a failure. It's not to scale, and this is called the PF, or potential functional failure curve. And basically, it tries to indicate roughly what types of signals you might get that occur as a failure progresses. Doesn't happen the same way for every machine, but in this case, for example, we see that ultrasonic monitoring has a very high probability of detecting a failure early, vibration analysis and oil analysis also. On the other hand, if you're looking to indicate a failure by seeing that parts are loose or that the machine is hot to the touch, you're probably not going to see that understand that a failure is occurring until very late in the cycle. These also line up with the different approaches. Reactive approach, again, is very late in the cycle. You're seeing things fall off the machine or it gets hot to the touch. Predictive maintenance is looking at the signals that are coming from things like ultrasonic monitors or vibration. And condition monitoring is also looking at the signals that you're starting to get off of some of these devices to get you a little bit earlier indication of when a failure might occur. So the earlier you can pick up the signals, of course, the more time you have to address that failure. The challenge being that there is also a cost-benefit trade-off to each of these different types of monitoring systems. Some are more expensive than others. It's almost no cost if you're just watching a machine and watching things fall off or seeing that it's hot to a touch. On the other hand, adding vibration or ultrasonic sensors can cost a fair amount of money, and to create those systems can also cost a fair amount. So what does that mean? So if we look at kind of just some examples of cost-benefit trade-offs of the PF curve versus some of the monitoring system, there's a unique profile for each asset and a unique cost of the prevention or the monitoring and a unique cost of the failure. So the longer you wait to address a failure, the higher the cost, but also there's a higher cost to try to detect early. And again, there's going to be an intersection for each different piece of equipment or each different machine. In some cases, the cost of the failure rises very rapidly the further you let it progress, but the cost of the prevention or monitoring may be low. And so you're going to want to implement a system that is very early detecting if the cost of that system is low to prevent that expensive failure. On the other hand, there may be some assets where the cost of prevention and the monitoring is very high, but the cost of failure is low. Think about maybe a small fan that's in the factory blowing cool air onto a piece of equipment. If that motor fails for that fan, it's not going to cause a big disruption, and it's only a few dollars to replace that fan, but putting a monitoring system onto that may be very expensive. That might be a good example of that one. The point is that throughout the factory, you're going to have multiple different assets with multiple different curves, and it may mean that you take different approaches to different pieces of equipment. A piece of equipment that has a high cost of failure, maybe it's a very critical bearing in a conveyor, and that conveyor produces a lot of parts per hour. That failure of that bearing could have a big cost on your factory. You may want to put in a monitoring system that costs a little bit more to detect an early failure of that. On the other hand, again, that fan example, you may not want to put monitoring in, and you may even be willing to take a run-to-fail approach on that. So the point here is we need to analyze the different pieces of equipment, assess the criticality, assess the cost of the failure, assess the cost of prevention and detection on that machine, and make those trade-offs as we go through our factory to understand where we might apply condition monitoring and predictive maintenance versus just take your reactive or preventative maintenance approach. So why should you care about this? Well, again, we talk about moving up from reactive and preventative maintenance in many cases to condition-based and predictive analytics. We talk about the importance of, on the critical pieces of equipment, detecting sooner rather than later. We talk about the cost-benefit trade-off and trying to find monitoring systems that reduce the cost of monitoring so that we have an ROI that's much more interesting for us to implement a monitoring system that detects failure early. So by doing all this, You can work with us to start to create solutions that will help you detect the failures sooner, to reduce the cost of the detection, which are an easy, low-cost way to get started with condition monitoring and predictive maintenance. This is really kind of the key point of what we're trying to get across, is to help you on this journey to condition monitoring, predictive maintenance, to find those and detect those potential failures early and more quickly to avoid these expensive and costly disruptions to your most important pieces of equipment. So what should you monitor? Again, we look at a factory and there's a lot of different places that we see customers implementing systems. Conveying systems, hydraulic power packs, even control cabinets, cranes, robots, motors. These are all kind of typical places that we see customers implementing condition monitoring systems. And the key thing here is that we want to reduce the downtime by monitoring these key mechanical, electrical, and other components to increase overall equipment effectiveness. Based on some research that we've done and that the packaging machine organization did, we see a couple different pieces of data here from the marketplace. Our data shows that the most common applications for condition monitoring are things like motors, pumps, fans and blowers, linear axes, gearboxes. The high proportion of this chart shows that customers are doing a lot of things on the motion side. That's confirmed by the data from PMI. Servo motors, induction motors, motor drives, and so on. Gearboxes are all the places where their customers identify that they implement or want to implement condition monitoring. So really, things where something is moving are the high potential places to do condition monitoring. They're not the only places. We see a lot of customers doing things like monitoring the inside of a control cabinet or non-movement type applications, but that's often a good place for people to start looking for condition monitoring applications. What are people monitoring? What are the indicators? If we remember the PF curve, the potential and functional failure curve, we talked about things like vibration, temperature, but also humidity and pressure. From our data, we see that a high proportion of people are doing vibration plus some other thing, temperature or humidity. And from the PMI data, the packaging industry data, again, people are measuring temperature, vibration. They're also doing things like speed and power consumption. So there's a lot of different things that you can measure on a machine, depending on what the application is, to start to think about figuring out when it is going to fail. But these are some of the typical ones. But vibration is often what we see in about 90% of the cases, the key factor that people are monitoring. So what are some solutions that are out there to help you detect those and find those indicators? So there's a wide range of smart devices that have condition monitoring built into their function in addition to the main function. In this case, we've got a photoelectric sensor, but it also will do things like measure the temperature, measure vibration, and measure inclination. Is it askew? Those are some of the things that you can get with specific smart sensors that have condition monitoring built in them. We have dedicated condition monitoring sensors that do vibration and temperature with options for ambient pressure and relative humidity. So maybe measuring pressure and humidity in a controls cabinet to see if moisture is getting in there. We have smart electrical drives and power supplies, which allow you to monitor their own condition. Are they getting hot? What is their power consumption? How many cycles have they gone through? And then finally, just general process monitoring sensors, things like pressure, temperature, and flow. Especially important, for example, in hydraulic applications to know what's the pressure and flow. Is there a filter that's dirty? And is the flow being restricted? So there's a wide range of sensors that are out there. But how do these sensors fit into a controls architecture? And where is that data being used? Typically, we find that customers are using the data in about 3 or 4 different ways. First of all, directly in the machine control system on a PLC or a CNC controller or some kind of motion controller, in a SCADA or an MES system. Also, a lot of customers nowadays are moving that data up to the cloud because they want to do the trend analysis and the analytics that allows them to start to move towards the preventative maintenance approach. And then finally, visualization. In most cases, customers want to do some kind of visualization with that data, charts, graphs, styles, and so on, so that you can, in real time, see what's going on in addition to not only gathering that data and doing analysis on that data. So the question becomes, how do we move the data from the sensors to these different places? Well, in our world, there's a couple different solutions. The first is built into the standard machine control system using an I/O link master, I/O link being the protocol that is used to take the data from the sensors to this master, and then the master can communicate up to your machine control system or the cloud or other systems using generally some kind of a field bus or field network or Ethernet-based network. So that fits into the more traditional controls architecture. Another approach is to use a dedicated edge and special processing controller called a condition monitoring toolkit, which allows you to do this processing and gather this data and do some analysis outside of the traditional control system and unburdening the control system from all that data and all that processing that's needed and dedicating the processing power in the condition monitoring toolkit to do the work for you. In this case, it has built-in tools for analysis and analytics, for anomaly detection, and for visualization and display of that data, all built into one. So is anyone actually doing this? We have experience with multiple customers that have actually successfully implemented condition monitoring. The first here is a customer using chain conveyor drives. They've got a long conveyor system for automotive parts. They actually had a catastrophic failure when one of the gearboxes failed, not only damaging the conveyor itself, but also damaging the parts that were on it, causing tens of thousands of dollars of damage. And so they decided to implement a condition monitoring sensor right here on top of one of the gearboxes. And very quickly, within a couple of weeks, we're able to actually detect another gearbox that was starting to go bad. And during a normal plant shutdown, we're able to replace that gearbox and prevent this catastrophic failure from happening again. You know, the key thing here is that they were given warning by starting to implement the condition monitoring system instead of having to live with the effects of a catastrophic failure and the downtime and the cost of lost parts and the cost of lost production. Another customer has implemented this system on a hydraulic power unit. And the challenges here is that these are often placed in hard to reach places. There's a lot of different parts of the system that need to be monitored. And in this case, they're monitoring vibration on a motor and a pump, for example. They're also monitoring pressure and flow in the hydraulic system itself. They're able to gather all that data, take it through a condition monitoring system, and be able to do a variety of different analyses. For example, detect when a filter is dirty, detect when the motor has a bad bearing or is starting to go bad. And so they're able to now use condition monitoring to address the failure points of this hydraulic power unit and again, prevent catastrophic failures and downtimes. Another case study here is on pumps. We have a customer that's used the condition monitoring sensor on a pump to detect when things are starting to go out of sync, when they're starting to get excessive vibration in the pump, either to replace a bearing or other parts of that. And the challenge is that often these pumps are mounted in places that are hard to reach or remote facilities where nobody goes on a regular basis. They don't want to have to send somebody up on top of a building or out in the middle of nowhere to go do that analysis and do that evaluation on a regular preventative maintenance cycle with that high cost. By using condition-based monitoring, they can avoid those service calls out there when there's nothing wrong with the pump and be able to do it on a basis of when the pump needs actual maintenance, when things start to need to be checked and monitored because you're starting to see excessive vibration, you're starting to see excessive temperature, and only then do the maintenance on the system. Another good example, non-motion based, is a controls cabinet. We have a customer who has had challenges with moisture getting into cabinets, causing problems with the electronics because somebody didn't close the door all the way during a wash cycle. So in this case, they're monitoring the humidity and the ambient pressure inside and can stop the cleaning process and stop the wash down process outside if they start to detect problems with ingress of moisture into the cabinet and prevent these moisture-related failures. Very important in, again, the world where you've got a lot of electronics because electronics and water and cleaning fluids don't mix well. Another example here is a welding fume fan. In this case, the challenge is that it's very hard to access this. It's very hard to replace broken parts. And so by using condition monitoring sensors on various parts of the system, on the fan housing, on the motor, on the bearings, they're able to start to detect problems, things like buildup of material on the fan, which starts to cause an imbalance, which can cause a catastrophic failure. They're able to, again, during a normal maintenance cycle, go in, clean that fan, and then restart the process without having to worry about a catastrophic failure. And in this case, because it's a welding fume fan, the whole operation has to stop if the fan fails catastrophically. And there's a long lead time to get the parts, long lead time to replace everything. So they're really saving themselves a lot of time and effort by being able to do the maintenance and the cleaning on the fan, which is a small cost compared to replacing the bearings and the motor and the fan itself in terms of a catastrophic failure. So how do we get started? We've got some advice for you based on some information from Control Engineering magazine. First step is to conduct a criticality analysis. What are the most important assets in your factory, and which ones are you going to lose sleep over thinking about that they might fail? Start to think about categorizing your assets. Secondly, think about the probable failures. What assets might fail? How has it failed in the past? How might it fail in the future? Manufacturers might be able to give you insights into that. Other factories who have similar equipment might be able to give you information on that. You might have your own experience. Next step is select the right solution. What kind of technology is going to help you address that potential failure before it happens? Do you need to monitor for vibration? Or is it pressure? Or is it temperature? Or is it a combination? What technology is going to allow you to figure out or detect early what might be your failure? What might fit with your control system? Do you want it to be built into your control system and controls architecture? Or do you want an external system that's an easy separate add-on that doesn't burden your control system with extra processing needs, extra data needs, and so on to bog it down? All that is part of the process. And then finally, start to execute and analyze. Start to look at the data that comes off that system. Start to see what are the trends and what's happening with that actual data. There's software tools that can do that. There's visualization tools that can do that. And start to see about how that's helping you or not helping you address these failures, and then go through the cycle again and start to scale up. What do you want to do for your first project? Start with a small pilot. Test it out somewhere. Find a machine. Maybe it is a critical machine, and start to work on that. Go through the cycle on the previous slide of doing the different steps of the analysis. Then work with your maintenance team, with your management, to start to explain the benefits of the condition monitoring approach and predictive maintenance approach. Document what you're seeing out there. Gather the data. Do the ROI analysis. Do the cost-saving analysis. And then grow it over time. Start to expand to other critical assets in your factory and expand on that success. So really, the key point here is that condition monitoring and predictive maintenance can really help you understand what's going on with your machines, provide early indicators and early warnings, and allow you to schedule the repairs and downtime and maintenance rather than the machine scheduling the maintenance and downtime for you. And that's a real key point, is that you start to move much more from a reactive approach to a proactive approach and dealing with these issues on your schedule rather than on the machine's schedule, and rather than having catastrophic failures that can dramatically affect your production, dramatically cause costs, dramatically reduce your overall equipment effectiveness. So thank you for your time and attention. Please feel free to contact me if you have questions, comments, and if you want to get started on the journey of more deeply understanding condition monitoring and predictive maintenance, discussing solutions, and seeing how you can get started. Thank you very much.